Okay. So today's lecture starts what's really going to be like one of the coolest sequences in the whole year. I'm hoping that the end of the year will actually be even more fun than this, but this was about as much fun as we had last year. So right now we're going to start talking about covalent bonding, and like really in earnest and in depth. So we had a basic definition of covalent bonding. Okay, so covalent bonding is really important for us because covalent bonding occurs within molecules, okay, covalently held, like covalent compounds or molecular compounds. So your essential questions for this unit or for this week are how and why do molecular compounds form and how are molecular compounds structured. And so we actually need to discuss the definition of a compound and what it is. But right now I just want you to think about covalent bonding in molecules, okay? And so molecules are the chemicals that compose us, right? Like we are composed of molecules. We're not made of metal, are we? Like do we conduct electricity? No, right? We're not made out of metal, okay? We'd be bad electrical conductors. So we're made of nonmetals. So what that means is that our bodies and even the things that we eat and consume, and most of the things that we interact with on a daily basis, right, are composed of nonmetals, which is kind of interesting because the nonmetals make up only a small proportion of the periodic table. Most elements, as you can see on the periodic table, are metals, okay? So, interesting, right? But we're not metal. And so this chemistry allows us to understand ourselves, and then in a really fun, coincidence, allows us to understand the food that we eat, and that's when the class starts to get really fun. I love talking about food and the chemistry of food, and I think we all do. So let's remind ourselves what covalent bonding is. So a covalent bond forms when two nonmetals share a pair of electrons, okay? That's your basic definition for a covalent bond. So you got two nonmetals sharing a pair of electrons. And then here's where things actually get really interesting. Nonmetals share their unpaired electrons so that those electrons can pair. With electrons from another nonmetal. Okay? So that's what's happening. Like, a more concise definition that I wrote on the board yesterday but that escaped me today is nonmetals bond to pair their unpaired electrons. Okay? That's a better definition. So nonmetals bond, or they form covalent bonds, in order to pair their unpaired electrons. And so we're going to talk about that over the course of the day. And we'll just continue on really from our example. We've been thinking a lot about water, and water is really important for chemists to understand. If a chemist doesn't understand water, that chemist is not a chemist. So here's water, right? So you've got H, O, H. Okay. And so where does that come from? Well, hydrogen has one valence electron. Oxygen, and it's not paired, right? Oxygen has 6 valence electrons, but 2 of them are unpaired, right? Then you got another hydrogen with an unpaired valence electron. And so what's happening here? So, like this electron here wants to pair, and so does this one, okay? So this atom, hydrogen, wants to pair its unpaired electron, and oxygen has an unpaired electron that it wants to pair, so they get together. It's sort of like an arranged marriage. And then you've got this hydrogen with an unpaired electron, this oxygen with an unpaired electron, and boom, right? They get paired up, okay? And if you think that the concept of an arranged marriage is antiquated, I'll tell you that my cousins had an arranged marriage. So my cousin by blood, Chandu Chithaluru, married his wife Ramya through an arranged marriage. It's like a big thing in India. I could have had an arranged marriage if I had wanted one, but didn't come to that. So, so anyway, so just that's an actual thing that still goes on today in India, and they're very happy. They have a son. They're awesome people. So anyway, so you've got boom boom. These guys are paired now. These guys are paired now. And here's the other thing that we really need to remember. All of these nonmetals bond in order to gain access to the same number of valence electrons as their nearest noble gas. So if you look on the periodic table, and we've done this in class, we're not doing it now because we have to use this board for other things today. Hydrogen is closest to which noble gas? Does anybody remember?
Helium.
Helium, good. How many valence electrons does helium have?
2.
Right. So if you look over here, you can see this hydrogen now has access to how many valence electrons? 2, right? And oxygen is closest to neon. How many valence electrons does neon have? Does anybody remember?
12.
Not 12, it's got 10 total electrons. How many of those are outer shell electrons?
8.
Good. 1s2, inner shell, 2s2, 2p6. So 6 plus 2 gives 8, okay? So look at oxygen. Count with me. Ready, set, we're going to count by 2s. Ready, set, go. 2, 4, 6, 8. So oxygen's got access to 8 valence electrons, just like neon, okay? And that's what this bonding accomplishes. So it pairs the unpaired electrons, which in and of itself gives these guys access to as many valence electrons as their nearest noble gas, okay? Generally. There are some exceptions to these rules, but I want you to memorize and take these to heart. They work the vast majority of the time. And we'll get into the exceptions probably when you get to AP Chemistry. We probably won't discuss them this year, and that's okay. So here we go. So we're going to go with a little table. So I'm going to make like a table from left to right. And we're going to start here. We're going to go atom. And then we're going to go electron configuration. And we're going to take a look at the number of valence electrons, and then the number unpaired, okay, valence electrons, and then we're going to look at some example molecules. Example molecules. Okay, so let's start with hydrogen. Hydrogen and let's start with hydrogen. So we've talked about hydrogen. Hydrogen has. Hey, Elijah.
So Dr. Jay, can I talk to you in a second?
No, I'm lecturing.
Alright, good.
Yeah, I'll see you during 2B. Very good. So, atom is hydrogen, and the electron configuration is 1s1. Okay? And the number of valence electrons, of course, is also 1. And the number of unpaired electrons is also 1. Okay. So some example molecules for hydrogen. So we've already talked about water, and I'll draw water a little bit differently. Like that. And then I'm going to draw another thing, which is hydrogen gas, H2, which is H, covalently bonded to H. You can also draw it like this. And what I'm illustrating here is that there are multiple ways to draw a covalent bond. So you can draw a covalent bond with a single line. You can also draw a covalent bond with 2 dots, okay? So it's really illustrated quite well here. 2 dots or a single line, they both indicate 2 electrons, okay? So the 2 dots obviously represent what kind of bond? Covalent bond. Also, this line represents a, and both of them represent how many electrons? 2 electrons. Okay, that's exactly what we're dealing with there. Good. So, okay, so hydrogen, 1s1, 1 valence electron, 1 unpaired electron, example molecules. Okay, and notice, right, this guy makes, so for as many unpaired electrons as he's got, and I actually have to erase this, number of unpaired / number of bonds. Okay, I want you to keep that in mind, because these guys are always going to make as many bonds as they have unpaired electrons, unpaired valence electrons. So hydrogen makes one bond here, one bond here, one bond to this oxygen. This other hydrogen makes one bond to the oxygen as well, okay? One bond for hydrogen. So, first atom is hydrogen. Second atom is fluorine. So fluorine is 1s2, 2s2, 2p5. Okay, so how many valence electrons does fluorine have?
7.
Wow, okay, pretty good. So we saw that 2 plus 5 gives 7. And we don't worry about these 1s2 electrons because the first shell is an inner shell. For fluorine, the outermost shell is the second shell. And we'll draw this in a second for chlorine so we can get a good idea of this. So 2s2, 2p5, it's got 7 valence electrons. Now it turns out that only one of these valence electrons is unpaired, okay? And we can see that when we draw the Lewis structure for fluorine. So when you draw the Lewis structure for fluorine, you draw F with 1, 2, 3, 4, 5, 6, 7 valence electrons, okay? You draw it like that. It's good to just put that little guy in there. 7 valence electrons represented this way, only one of them is unpaired, so it can only make one bond. So when fluorine bonds to hydrogen, you get HF. This is hydrofluoric acid. It's really important in the semiconductor industry. So it's important in the manufacture of all of the computer chips that we use in our computers, bless you, or in our cell phones, or sometimes in our smartwatches, right, if we have smartwatches. So very, very important chemical. Also really, really reactive. This thing will react even with glass, okay? Very few chemicals react with glass. This bad boy will, all right? Don't get that on yourselves. It's very, very dangerous. Another thing that we can show is fluorine bonded to itself. So fluorine making one bond to another fluorine. Okay? There we go. F2 gas. That's F2 gas. Okay, fluorine gas. So if we remember, our diatomic gases consist of 2 atoms, right? 1 atom, 2 atoms, okay? And this fluorine makes sense because this fluorine wants to make one bond, this fluorine wants to make one bond. Oh, they just make one bond to each other. Okay, let's look at a very similar example. Chlorine has the electron configuration 1s2, 2s2, 2p6, 3s2, 3p5. Okay, so how many electrons are in the outermost shell for chlorine? Let's all respond together. Okay, take a look. Which shell is the outermost shell, and how many electrons are there? On the count of 3. 1, 2, 3. 7. Okay, so the third shell is now the outermost shell, and you've got 2 plus 5 equals 7. So 7 valence electrons. Boom. And chlorine looks, in terms of its Lewis dot structure, just like fluorine. So 1, 2, 3, 4, 5, 6, 7. It's got 1 unpaired electron, and here are some molecules. So it also likes to bond to hydrogen. So it does, and it forms HCl, right? This guy's important. We couldn't live without him. He's stomach acid, okay? So hydrochloric acid lives in our stomachs and allows us to break down proteins. If we didn't have hydrochloric acid there, the enzyme that does that protein breakdown, which is called pepsin, wouldn't be able to function. So very important for life. Chlorine can also bond to itself, so Cl-Cl. And that's chlorine gas. It's yellow, and it's deadly. So if you breathe that in, you might kill yourself, okay? Chlorine, not for humans. Okay, not the gas at least. Chloride ion, totally fine. Interesting, right? So, okay, so what's going on here, right? The part where the part of this like presentation where we sort of stuttered was right here, figuring out the number of valence electrons. So let's back up and kind of go back to our atomic structure a little bit and think about what chlorine is made up of. Now chlorine is atomic number 17, so it's got 17 neutrons, or sorry, 17 protons, which I'll represent this way. It's got an atomic mass of 35, which means that it commonly has 18 neutrons. So I'll go 18 with a little n, and I'll put a circle there. These guys represent the nucleus of a chlorine atom. Okay, that's our nucleus. So let's go ahead and build shells of electrons. So first shell has 2 electrons in it. Electron, electron. Boom, boom. Second shell has 8. Electron, 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 electron. Okay. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Third shell has 2 plus 5 equals 7 electrons. So we go electron,